So I just finished my first semester of the P-Chem sequence in my degree, and the thing about P-Chem is that it's the field of chemistry that I know the least about, at least I knew the least about going into it. Let's do hard mode. That means I had the most amount of questions going into it. In the coming days before the semester started, I started writing down a list of the absolute stupidest questions I could think of to ask my professor during her office hours. How does this mode work? Okay. So this included stuff like, what's actually going on when you tear a piece of paper in half? Or even, can a gaseous form of hydrochloric acid have a pH? Or, in other words, can gases be acidic? Now, my professor gets really annoyed every time I ask something this stupid because, quite frankly, she doesn't really know how to answer these. And I don't blame her. I wouldn't know how to answer them myself either. So one of the questions I asked her in her office hours had to do with the electron C in blocks of transition metals. So take something like a block of pure iron. I wanted to ask how exactly this could be explained by the bonding theories we learn in chemistry. Specifically, how the electron C can be explained through things like molecular orbitals. So when you have a block of pure transition metals like iron, the valence electrons between them aren't quite shared the same way as they are with most chemicals. Basically, the valence electrons of iron atoms become so delocalized from their parent nuclei that all the valence electrons in the sample of iron will jump from atom to atom instead of being shared by one or two. Hold on a second. Go chop some. This is called an electron C because it's often represented as a mass of iron cations being held together by one large mass of delocalized negative charge. And if you've ever taken E&M or Physics 2, you'll know that magnetic fields are caused by moving charges. This is why blocks of iron are magnetic, actually. But here's the thing. This got me thinking more about how we describe bonding in other types of compounds. Specifically, it got me thinking about ionic salt crystals like sodium chloride and whether or not they have molecular orbitals, or if they too have an electron C. I asked this to my professor, and her answer was a bit disappointing, I gotta say. She said that it isn't quite that they don't have molecular orbitals the same way that compounds like benzene do. Not quite. It's more so that it's easier and more reliable to describe them as having ionic bonds as predicted by Vesper theory instead. It's easier to make predictions about ionic salt crystals like sodium chloride with Vesper theory rather than molecular orbital theory. That brought me to the realization that, well, everything I learned in my life is a complete lie, and nothing is real. Yep, welcome to physical chemistry. So that's a lot of info to just randomly dump out. Let's take a few steps back and try to get a grip on what I actually want to talk about. For starters, this video is actually about scientific models and how the way we describe stuff in science isn't meant to be taken as literally as you might expect. Oh, it's this. Oh, neat. People generally like to think that scientific facts are the end-all, be-all of truth, when really there's a bit more nuance to it than that. The bottom line is that in science we often can't accurately or fully describe nature because it's frankly just too complicated. So instead we often just simplify it down to these things called models, which are basically cartoonized versions of reality. A good example would probably be the planetary model of an atom. So if you've ever seen a picture of an atom, it probably looks something like this, where you have a nucleus in the center with a couple of electrons moving around it. And this is called the planetary model of the atom, because it looks sort of like the planets of our solar system orbiting around the sun. Plot twist though, atoms don't actually look like that, not even close. In fact, this model is borderline lying to you with how inaccurate it really is. But that's just the thing, right? So, we have these models, which aren't real descriptions of reality, but they're good approximations, and we use them for both teaching and making predictions. And that's kind of the point. But if we want to describe what molecular orbitals really are, and before we can really get into why molecular orbitals don't really exist, god damn it, I have to take you through basically the entirety of General Chemistry 1 and 2 in that case. Which, strap in, this is going to be a bit of a long ride. So, the hardest part about early chemistry courses, in my opinion at least, is that you start to learn a bunch of information that you don't really have the context for to really appreciate or understand. You go over things like atomic orbitals, electron orbitals, I should say, electron configurations, quantum numbers like n, l, and m, things like that. And you don't really have the context to fully appreciate those sorts of things yet. Quite simply, a lot of the early content in General Chemistry 1 and 2 for first-year chemistry students is really, put simply, we're trying to describe what atoms actually look like. And spoiler alert, they don't look like the planetary model. Not even close. In fact, atoms look closer to this. Okay, but what is that? What are we looking at here? Well, we gotta start off with some quantum mechanics. God, I am getting my ass kicked by this guy. Yeah. Before we can circle back to molecular orbitals and why they don't exist, or quote-unquote don't exist, we gotta get a better understanding of what atoms really look like. And to do that, let's start off with what parts are true of the planetary model of the atom. God damn it. So, the planetary model is correct in that you do in fact have a nucleus, a positive charge with some neutrons in the center, and you do in fact have some electrons moving around the atom, or the atom's nucleus. But that's more or less where it stops. Atoms are, by their very nature, quantum mechanical, and thus need to be described using quantum mechanics. So, let's go over a quick quantum primer. God damn it. Oh well, that's what I get for commentating over this. So you remember all that stuff from early Gen Chem where we talk about electron configurations? Yeah, what exactly is going on there? Well, an atom has what's known as electron shells and electron orbitals. Orbitals are just the parts of space where an electron probably is. Shells are essentially just the places where orbitals are kept. Quick reminder, none of this is technically quote-unquote real. We just use this as an explanation about the nature of atoms. As an atom becomes more massive, that is to say, as it increases Z, its proton number, it will have a higher amount of electron shells corresponding to the principal quantum number n, which is just a whole number of at least 1. The higher the principal quantum number n is, the more orbitals that shell will fit. But it's important to remember that each orbital itself will only hold a maximum of 2 electrons. Can I build beds yet? Oh, I should probably, feed this one guy I just captured. Oh, I actually have to beat that guy at Knucklebones. God damn it. So let's take helium as an example. The helium atom only has 1 electron shell because its N number is 1. It's in the first row of the periodic table. That 1 electron shell itself only holds 1 single orbital, the 1s orbital. And that 1s orbital just so happens to have 2 electrons in it because it's helium. It's element number 2 on the periodic table. 2 protons, 2 electrons. Because helium only has this 1 shell and orbital, and it just so happens to be full, this means that the helium atom itself is super duper stable. If you've ever wondered why helium is element number 2, and yet it's all the way on the opposite end of the periodic table with the noble gases, this is why. Its one and only electron orbital is completely full, and it's as low energy as it could possibly be. Alright, so far with that, we know that an atom should look something like this, more or less. Where you have these invisible shells that can hold a couple different orbitals where where each orbital can hold a maximum of 2 electrons each. And I have to stress, these orbitals are where these electrons can probably be found. Notice how I keep saying the word probably here, and that's because QM is inherently probabilistic. We can't actually determine the exact locations of electrons for a couple of different reasons. And if you've ever... Wow, I keep getting 4s. If you've ever read anything in popular science about quantum physics, you probably know where this is all going. And take that. Oh, that'd be so useful here. Oh well. Now, quantum mechanics itself as a field is governed by a few principles as follows. Let's go over a couple of them, shall we? Number 1, electrons will fill up an atom's orbitals and shells from lowest energy to highest possible energy in that order. This is called the Aufbau principle. Yay, I did it. Think of a Jenga tower. You can't build it by placing the pieces from top to bottom. You need to put the pieces on the bottom first and then move higher. That's what's going on here. Yay, a tarot card is unlocked. Whoopee, whatever. Number 2, electrons can act as both a particle and a wave. So what that means is that it's better to think of electrons as an excitation of energy in a field rather than an actual solid floating object that, you'd be more accustomed to at the macroscopic scale. Now, as I say that, I realize that itself is a deeply complicated topic that gets into field theory, but I can't really go that far in this video, that's a bit out of the scope. The important takeaway from this principle is that just know that electrons aren't really solid physical objects the way that you might imagine them to be. They're not point particles. They're more like packets of energy, packets of negatively charged energy, that is distributed over a certain area of space. That's how electrons behave. Moving on, number 3. It is impossible to know both the position and the momentum of an electron at any given time. This is known as the Heisenberg principle. This principle itself is sort of the basis from the most famous conclusion of the Schrödinger equation, which is called superposition. We'll talk about that more in a bit. Number 4. No two electrons can have the same quantum numbers. Or, put it another way, no two electrons can occupy the exact same space. This is called the Pauli exclusion principle. Again, that's a huge amount of extremely profound theory that I'm just skipping over. But to give a visual representation, which, by the way, is still not completely accurate or completely true, remember that, an atom sort of looks like this, where you've got a nucleus in the center and these fuzzy highlights of space around it where the electrons can be. Each of these fuzzy highlights is an orbital, which, as I said before, can hold a maximum of 2 electrons. Unlike orbitals, by the way, shells aren't physically represented here, because they're just not really something that you can see. Shells are just stacked on top of each other. Think of just more orbitals on top of other orbitals. I should probably start making food for this guy. Okay, that's enough of the physics. Let's get into the chemistry, shall we? Okay, so now we know what an atom actually looks like. Kind of. I can't stress this enough, but what we're actually looking at, I didn't mean to go there, oops. I can't stress this enough, but what we're actually looking at is just an approximation. It's a model. I mean, yes, everything I said earlier is true, but it's sort of the point of this video to show how it's impossible to accurately represent specific phenomena in science. It's impossible to model the atom perfectly. So an atom has electrons in a particular configuration, and these electrons will occupy orbitals in increasing energy levels in a predictable pattern. Cool. So chemistry is all about understanding how, where, and why these electrons move. So here's the thing about most atoms. Their electron configurations are not perfectly stable. Ooh, yay, a hammer. I love these things. Oh, I actually have to focus now. This is going to be difficult. Yeah. To be more specific, because most elements of atoms on the periodic table have more electron orbitals than they do actual electrons, this means that for most pure elements, their electron orbitals are going to be only partially full. Why is that a bad thing? Well, you see, atoms actually kind of prefer this all-or-nothing strategy. Oh, wait, what the hell's going on here? Oh, it's this bitch. But yeah, like I was saying, having partially filled orbitals is actually worse than having completely empty ones. So, let's say that you have something like sodium, which is in the group 1 elements. I think that's the alkali metals. Yeah, it's the alkali metals. Sodium is in group 1, which means it has 1 valence electron in its outermost shell, outermost orbital at that. But remember when I said each orbital needs 2 to be full? Well, this outermost orbital in sodium is only half full. Okay, so, like I said earlier, atoms prefer an all-or-nothing strategy. Let's see why that's a problem for things like sodium, which is in the group 1 elements of the periodic table. So, sodium only has 1 valence electron. That means a valence electron is just an electron in the outermost shell, orbital, whatever, of an atom. But remember what I said earlier, orbitals need to have 2 electrons in order to be full. This means that sodium's outermost shell is only half full, which is a bit of a problem. Because this outermost orbital of sodium is only half full, and it's just a lot easier for the atom to lose its electron altogether, it's just going to do that. It's more energetically favorable to have a completely empty orbital than it is to have a half-full one. And the reason why sodium is so willing to get rid of this 1 electron is because it's just more energetically demanding to take on another electron. There's this thing called electronegativity. It's a trend in the periodic table. It increases going to the right and up, and sodium is on the far left of the periodic table. So this means that sodium is much more willing to... I don't want this thing at all. This means that sodium is much more willing to just get rid of its one electron and go into the cationic form. That's just a lot more energetically favorable. This is why sodium typically exists in a cationic form. Now, obviously, because of E&M, things cannot just have a pure positive charge and float around. That's not actually how things work. But this video isn't about electrodynamics. It's about chemistry and models and stuff like that. So, physicists D&I. So in order to complete the octet rule, atoms will either share their electrons, their valence electrons, in order to reach a full octet in their outermost shell, which is called covalent bonding. Get it? Covalent, they're sharing their valence electrons. Or, alternatively, they will give up their electrons and turn into a charged particle, either positively or negatively charged. In this case, the two atoms will stick together due to the electromagnetic force holding them together like magnets. So think of like a positive charge and a negative charge. They both attract each other. One gave up its electrons and became positively charged. The other took up those electrons and became negatively charged. This is ionic bonding. And this is how the Vesper theory of bonding works. So, valence bond theory is pretty useful for teaching undergrads about introduction to chemistry. And as I said before, it isn't wrong per se, but it's also just not correct. Right off the bat, we already know what really gives atoms their stability. It's the quantum mechanics principles we talked about earlier, with electrons filling up the maximum amount of orbitals that they can have. Not necessarily because they specifically have to have 8 in their outermost shell. Additionally, if valence bond theory were meant to be taken literally, that would mean that you would assume that none of the noble gases over to the far right of the periodic table would ever be able to do chemical bonds, which just isn't true. We have chemicals like Xenon hexafluoride for a reason. Even the idea that Vesper theory is only true for naturally occurring molecules is incorrect, because you can see plenty of examples that break the octet rule, things like metalloenzymes in heme, or vitamins like vitamin B12, etc. Hello, Cat Dad. And so far, this is only talking about how compounds make bonds. We haven't even talked about why conjugated pi bonds of organic molecules have such unique properties, or why molecules take the shape that they do. Oh, I'll just leave it as the default. Let's take a quick detour on conjugation, actually, because that's a pretty interesting thing. I'll give you a gift, why not? Big gift, because you've stuck out with me longest. So, in organic chemistry, another way of saying a double bond is a pi bond. And there's a reason for this. It's because these bonds include electrons that occupy the pi orbitals of these two electrons, and these two pi orbitals will just start to overlap, which will form a double bond. When you have long organic compounds with a bunch of pi bonds in an alternating sigma-pi bond fashion, we call this conjugation. This is because, technically speaking, the electrons of these double bonds can actually be in either place. They can actually just swap their locations, and the real molecule is actually a long distribution where you have a possibility of charge distributed across the entire molecule. It looks like this. This induces some of the stuff we talked about earlier in QM, where those pi and sigma bonds can actually alternate. But the actual structure of the molecule itself involves a distribution of the electric charge across all of the conjugated bonds. In other words, the electrons across a chain like this, in a fatty acid or something, actually exist across the whole area all at once. This is quantum mechanics creeping up into your chemistry. It's literally the superposition principle I mentioned earlier. The different ways that these electrons can configure themselves in these sorts of conjugated molecules are called resonance states. And it's because of resonance that some molecules experience a noticeably higher level of chemical stability than others. Take, for example, conjugate bases or acids that are way more stable in their original protonated forms. Something like ethoxide, for example. So here's where we're at right now with our model of electrons. Oh, I can't actually do this yet. Wait, can I? No. So here's where we're at right now with our model of electrons. We have Vesper theory and the octet rule that are good at explaining reactions of small molecules made up of elements from the first 3 rows of the periodic table. This model breaks down as soon as we get into anything with involving transition metals, and it can't explain noble gas chemistries. It also can't explain why electrons behave so differently for large molecules when conjugated with other double bonds that use pi orbitals. This last point especially calls in the need to have a new theory of bonding to explain what we're seeing in the data. And I'll do a sermon right now. So, where do we go from here? Well, if we go from atoms to molecules, then the natural thing to do would be to start looking at orbitals from a bigger perspective than just individual atoms. Now with that, finally, we can start talking about molecular orbitals. So, the easiest way to think about Mo theory, which is what I'm just going to be calling it now, molecular orbital theory, Mo theory, is that molecular orbitals are just atomic orbitals, but they are in reference to the entire molecule, rather than just the nucleus of one individual atom. For simplicity's sake, we only consider the outermost orbitals of the atoms. So imagine you have one atom, and it's got an outermost orbital where some valence electrons are spinning around in quantized states. Neat. You bond it to some more atoms with their own outermost orbitals, and according to Mo theory, this group of bonded atoms now have a set of valence electrons that occupy some molecular orbitals, which mathematically are the sum of the wave functions of collective atomic orbitals. This is called linear combination theory of atomic orbitals, or LCOW for short. The math here is pretty advanced, and I can't actually do it myself. Please understand, I'm just a puny little undergrad. I'm currently learning this stuff as I'm teaching it to you guys. But essentially, you have two nuclei bonded together with two electrons floating around the system. So imagine like two H's bonded together. We want to find a wave function that models this whole system as a sum of the wave functions of the individual electrons with their associated nuclei. And the formula for that would look something like this. I'm not going to read it out, I'm just going to put a picture of it on the screen here. Now, if you've ever read anything about popular science for physics especially, or quantum mechanics, you've more than likely heard about the Schrödinger equation. That's what we're talking about here. The Schrödinger equation is just a way to solve for the wave functions of an atom. The wave function itself just shows the probability density distribution of where you can find those electrons from earlier. Remember what I said about them being probabilistic and having a distribution of charge over a region of space? That's what we're talking about here. After solving the individual Schrödinger equations and normalizing them, you can solve for the energy operators using the variational theorem. What that means is essentially you can make an educated guess on what the wave function will be. The reason why we have to make an educated guess when solving the Schrödinger equation is that for anything with more than just one electron, the Schrödinger equation itself is too complicated to solve. We can't do that math analytically, we have to do it computationally. In fact, this whole process of using the variation theorem begins with assuming that the nuclei of both of the involved atoms in this molecule are too big and heavy to actually move around. So their kinetic energy terms go to zero because they're just assumed to be stationary. Again, that's not really what's going on. Obviously, us physicists and chemists know that the nuclei are moving, but we have to make these approximations to make the math easier. So we assume that the nuclei are stationary and their kinetic energy terms in the Hamiltonian goes to zero. With that said, the derivation looks sort of like this. I'm going to be referencing this book right here called Symmetry and Spectroscopy by Daniel C. Harris and Bertolucci. It's a really good book. I highly recommend it if you are interested in learning more about spectroscopy. The most important part of this derivation is S sub ij, which is defined as such. And I'll just show another thing right here. Basically, it's defined as the area where the wave functions for A and B overlap. If these two regions of space are completely overlapping, then we call that unity. The two orbitals have completely hybridized with each other. I also want to point out how this section of this textbook literally starts off with a disclaimer saying that linear combinations are not even what molecular orbitals actually are. It's literally just a way of simplifying the math and helping us describe them. It just goes to show that none of this is meant to be taken literally, since it's just how we model real life. The bottom line is that mathematically, Mo theory can be described as the sum of the wave functions for each atomic orbital participating in a molecule. Now that we've gotten all that out of the way, and I want to break it again. Now that we've gotten all that out of the way and we understand molecular orbitals from a mathematical perspective, and also from a theoretical perspective, they're just, electron orbitals considering the entire molecule rather than just a single nucleus, we can finally get to using molecular orbitals to describe chemistry and chemical reactions. So let's start doing some chemistry with Mo theory, shall we? For starters, let's talk about structure and symmetry. Vesper theory lets us predict the shape of a molecule based on the number of bonds and number of lone pairs that it has. But this is limited in use because, again, only so many chemicals actually follow the octet rule. Let's take Xenon hexafluoride again as another example, because that's another molecule that... Oh, okay, it's you again. But yes, Xenon hexafluoride. It's a molecule that doesn't follow Vesper theory, and according to Vesper theory, it shouldn't exist. We can explain its shape and its existence by plotting a molecular orbital diagram and showing the octahedral structure of this molecule. There's this really good webpage I found on the Chemistry Stack Exchange by this one guy who puts it a lot more eloquently and a lot more in-depth than I could. I'll link it below if you want to read more. Ow. But essentially, the octahedral symmetry and structure of this molecule can be predicted using molecular orbitals by combining the individual atomic orbitals of the 1 xenon and the 6 fluorine ions, and then constructively combining them all together to... I am low on health, damn. To make a single, well, not one single molecular orbital, more like a bunch. Molecular orbitals themselves can overlap constructively, which will form a bonding orbital, or they can overlap destructively, which will form an antibonding orbital. When I say constructively versus destructively, remember what I said earlier about these orbitals being defined by their wave functions? Well, each wave function is just that, a wave. So if you have two waves that are inverses of each other, where the peaks are lining up with the troughs, then those two orbitals, once they overlap, will overlap destructively. The waves will just cancel each other out, and this forms an antibonding orbital. Antibonding orbitals are what causes bonds to break, by the way. Conversely, a bonding orbital is what happens when the peaks line up with peaks and troughs line up with troughs. You form a more exaggerated wave instead of destroying it. This is what forms the basis for molecular orbital theory predicting bonds in chemical reactions. This is the model that chemists, especially computational ones, use to predict chemical reactions theoretically. There's a lot of work in computational chemistry that uses these molecular orbitals, and they use them to predict, like, what reactions will cause constructive versus destructive overlap. Under Mo theory, chemical reactions are just the interactions between the molecular orbitals of two or more molecules. And I should also stress, they are something called the frontier orbitals, not just any. Okay, I'm realizing as I'm recording this that I just forgot to mention something important. When you do that alcal method from earlier, as you add up the atomic orbitals, it's in a 1-to-1 ratio. So, for example, if you have 6 atomic orbitals, those will all add up to 6 molecular orbitals. Just thought I should probably mention that. So we add up all of the atomic orbitals into an equal number of molecular orbitals. So like I said earlier, let's take this molecule, for example. It has 6 atomic orbitals, so we add them up to make 6 molecular orbitals. If we plot a diagram of each orbital only holding up to 2 electrons, we will see that not all of the molecular orbitals are filled, even though all the atomic orbitals would be. Hello again, Cat Death. Oh hey, I get to read people's minds now. Neat. Looking at this plot for, I think it's hexatriene or something like that, it's like basically hexane with like 3 pi orbitals, 3 pi bonds attached to it. Looking at this plot that I'm going to be taking from this one organic textbook that I really like, it's the one that I use in my own university. I'll link it below if you want to like read it for yourself. It's pretty good. Basically, you can see that there are 3 orbitals that are actually full and 3 that are empty. Psi 3 in this example is the most important one. That is called the highest occupied molecular orbital, or the HOMO for short. And no jokes. No HOMO jokes. The one directly above that is called the lowest unoccupied molecular orbital, or the LUMO for short. So this textbook, which I think is by Klein, I want to believe, it has a really good example for something called a pericyclic reaction, which is very easily explained by molecular orbital theory. I'll put an image of it on screen, don't worry. Basically, what's going on here is that the HOMO of butadiene, which is Psi 2, interacts with the LUMO of ethylene, which is Psi 2 as well. The LUMO of ethylene is lower energy than the HOMO of butadiene. So what ends up happening is that these 2 orbitals will interact with each other, and the electrons from butadiene's HOMO will go to ethylene's LUMO. This will form a reaction where the two molecular orbitals will line up with each other and then form a molecular bond. This is how all organic reactions play out. Or more accurately, this is how we describe all molecular reactions in organic chemistry, at least, using molecular orbital theory. And there's something of interest to note here with this specific reaction in particular. Notice how, well, I guess it's not this specific reaction, but I'm using this as an example. Notice how this only happens because the two orbitals from the HOMO and LUMO of the respective reactants just so happen to line up in phase. Oh, I think I might have forgotten to mention that. Molecular orbitals come in pairs of phases, so one will be in +1 phase, one will be in a -1 phase. This is basically the exclusion principle I mentioned earlier. The final quantum number is the spin quantum number, ms, I believe. And it can either be +1/2, -1/2 in atomic orbitals, and it comes back with a vengeance here in molecular orbitals, especially in p orbitals, which always have these two phases. In order for a reaction to occur, not only do the LUMO and HOMO have to have varying energy levels between each other, they also need to be within the same phase. If we were to take an example where the two molecules may have lower energy but are out of phase, then there will be destructive overlap and no reaction will happen. That would look like this. One way to get around this out-of-phase problem is by introducing UV radiation, or just any sort of radiation with an appropriate energy level and wavelength, and exciting the HOMO of one of the reactants, and forcing the electrons in that HOMO to jump into the LUMO of said reaction. It looks like this, where you add some UV radiation, and then one of the electrons, but importantly not both of them, will go into the LUMO. And that LUMO will be in an opposite phase, and hopefully will line up with the phase of the reactant you want it to react with. Said in a more normal way, if you add light to the highest occupied molecular orbital of a reactant, or molecule, I should say, one of its electrons will absorb the energy from that photon and jump into the next energy level. This is called an excited state, and under normal circumstances, that electron would just fall back down into the previous energy state that it was in, because it's more stable. But if that energy state is higher than the HOMO of a different molecule, and that molecule's HOMO is, in phase appropriately with this molecule, and they interact, then a molecular reaction will occur. This is called photochemistry, or photochemical catalysis, and it's actually a huge branch of chemistry that I actually worked in for a while. It's really interesting. I definitely recommend looking into it more, because photochemical reactions are just so goddamn cool. There's a lot of great possibilities that come from it. Okay, but that doesn't answer the whole point of this video. Why molecular orbitals don't exist. I keep saying this because it's so important to understand, but nothing about these theories of bonding and electrons is meant to be taken 100% literally. The general public tends to think that just because something is a scientific fact, that means it is 100% carved in stone and completely infallible, when that's just not the case at all. Okay, if some research makes it through peer review and then gets published in a journal, then supposedly it is a fact carved in stone and cannot be disputed. But that's just not how science works at all. As a scientist, your job is to understand that just because something is published doesn't mean that it's the end-all be-all of knowledge. It doesn't mean that that paper is necessarily right. All it means is that for this specific scenario, these scientists did an experiment, and their data led them to these conclusions. In science, we use inaccurate models all the time because nature is just far too complicated to ever truly describe perfectly. Remember what I said earlier about the Schrödinger equation and wave functions being too difficult to solve for a system that involves more than just one electron? Well, here's what the math looks like if you were to try and do that. This is what I say when molecular orbitals don't exist. If you were to actually look at a molecule of benzene, it wouldn't look like this, it would look like this. In all seriousness, benzene doesn't actually have a giant massive orbital covering it. It just has a probability density distribution of outer electrons which randomly move across the entire structure. That's it. But generally, those electrons just stick to similar places, and we just look at the areas of the molecule where those electrons are more likely going to be. And the places that they end up being are just wherever their potential energy is minimized. That's why they're so predictable. And I highlight this because it's important to remember that as you learn things in science, you need to separate what is the truth from what is just a tool we use to find the truth. Molecular orbitals may not be real, but the molecules that they describe and the reactions that they predict are. The drugs that they help us discover are real. The syntheses they help us design and test our hypotheses are real. Molecular orbitals are as real as the truth that they guide us to, and the same can be said about any model in science. And yeah, that's all I had. Thanks for watching. See you next time.